Yeah, when it's time, please let me know that I'll get started because I'm not able to see you or anything. I'm just seeing my screen itself.
Yeah,
We
Sayed.
can
Yeah,
use that
Okay,
much.
we'll start
okay,
shortly.
okay, no problem.
Abhishek,
Yeah, yes, sir.
I think we can wait. So if Dr. Sayed agree, then we can wait for 2 to 5 minutes, na? Because our main purpose is students should learn.
Yeah, yeah,
Yeah,
no
Sayed,
problem. I
what is
can
your
wait. No
suggestion?
problem at all. No problem.
So ultimately, you have to take the decision, Dr. Abhishek. You take your decision. Huh? So this is
yeah,
for
yeah,
my
sure.
advice.
We will wait for a few minutes and then we can start.
Yeah.
Yep.
So I think we have enough
Yeah. Yeah. Yeah.
participants. We can start. And good morning to all the faculty members, research scholars, undergraduate students who have joined us today on this Sunday morning for the symposium on mechanical testing at small length scale, which we at Department of Metallurgical and Materials Engineering at MNIT Jaipur is proudly organizing with Industron Nanotechnology Private Limited. I welcome the guest speaker of today's symposium, Dr. Saeed Asif, who is joining us today from Minneapolis, USA. And it must be, I should say, rather late evening or late night for you, Dr. Asif. So I thank you for taking time for us and conducting this symposium. So to start the proceedings of the symposium, I firstly request Dr. Rajendra Kumar Goyal, Head of Metallurgical and Materials Engineering Department, for his opening remarks. Professor Goyal.
Okay. Thanks, Dr. Abhishek Tripathi, and good morning to one and all. So, on behalf of the Department of Metallurgical and Materials Engineering, it is my great pleasure to welcome our today's speaker, Dr. Syed Asif. As you know that he is well known in the area of nanomechanical testing. Thanks, Dr. Syed Asif, for planning this activity jointly between your institute or your organization in Industron Nanotechnology and Department of Metallurgical and Materials Engineering, MNIT Jaipur. And I also thanks to your team members who are behind this activity. So, dear friends, as you know that when we reduce the size scale from, you can say, millimeter to micrometer, micrometer to nano scale, so how the thermal, mechanical, electrical, optical, magnetic properties are changed. So very interesting phenomena you can observe when you reduce the size, particularly below 100 nanometer. And really all the properties are changed that most of you have already studied in UG and PG classes. So I will briefly discuss some changes in the properties, how the properties are changed. For example, you take the example of melting point. When you reduce the size from, you can say, 50 below 50 nanometer, or particularly when the size is around 2 to 10 nanometer, the melting point of the metals may decrease it is unbelievable, but may decrease about 50 degrees Celsius to 200 degrees Celsius. Then their bulk melting point. So it is very interesting. And the question is how the melting point is reduced. So that you can see in many textbook or research papers. Similarly, electrical conductivity may decrease, may increase. It is very interesting. So in most of the cases, electrical conductivity is reduced. But in exceptional cases, electrical conductivity is increased. Thermal conductivity is reduced. And if you see the magnetic behavior, that is also very interesting. So when the size or domain size of the order of, you can say, or particle size, not domains, of the magnetic particles is about 30 to 50 nanometer, you will see that their magnetic properties are dramatically increased. And similarly, mechanical properties that we have already studied in the UG levels, Hall pitch relationship. So when the grain size is reduced from micrometer to sub-micrometer or nanometer, how the hardness, yield strength is significantly increased. But if you reduce the size below 30 nanometer, again the reverse phenomena you will get. Instead of increasing the hardness and strength, you will see the decrease in hardness. But again, the hardness will be more than the bulk hardness. So my question is that here we will see the phenomena of increasing the properties or decreasing the properties with size scale. But the question is, how will you measure, particularly hardness? If you want to measure the hardness or if you want to measure the strength, how will you hold the nanomaterials? If you have the nanofibers, if you have the, you can say carbon nanotubes, the question is, how will you hold? Can you measure the hardness or can you measure the strength of the pure isolated nanoparticle or isolated nanotubes or nanowires? It is really interesting as well as challenging. So I think in today's talk to be given by Dr. Syed Asif, we will learn this interesting thing. So particularly about the nanomechanical testing. So I hope that we all will enjoy this talk. So it is my request to please listen and enjoy this talk for maybe around 1 hour now. Then if you have some question in your mind, definitely we will ask to Dr. Syed Asif. Thank you. Thanks, Dr. Abhishek, for giving this opportunity to me.
Thank you, Professor Goel, for your opening remarks. I request all the participants to kindly ask their question in the chat box while the symposium is going on. And at the end of the symposium, we will look questions. So with that, I now introduce our guest speaker for today, Dr. Syed Asif. He is currently the managing director and founder of Industron Group of Companies. He has over 30 years of experience in designing and developing nanomechanical testing instruments. Before in Industron, he was director of R&D at Bruker Nanosurfaces and Hysotron. He has completed his PhD from the prestigious Oxford University in Material Science and hold masters and bachelors from Indian Institute of Science, Bangalore. He has 22 active patents in nanomechanical instrumentation and over 120 publications, numerous invited talks and webinars. He is, you can say, one of the pioneers in in-situ nanomechanics inside transmission electron microscopy, scanning electron microscopy, and Raman microscopes. He has won several awards in his career, has won around 100 awards, also Microscopy Today Innovation Awards, and was instrumental with SBIR funding and National Diabetics Awards for Hysotron. Under his leadership in Industron, Nano grew a nanomechanical testing instrument for graduate and undergraduate education and research was developed in India. He is currently active in promoting nanomechanics curriculum worldwide. He is also a member of Materials Research Society, American Ceramic Society, the Minerals, Metals and Materials Society, that is the TMS. He is also an avid collaborator of research with academic and research institutions around the world. So it is our great pleasure to have Dr. Saeed Asif here with us. With that, I now invite Dr. Asif for his lecture. Dr. Asif.
Thank you very much, Dr. Abhishek and Dr. Professor Goel. Uh, Thank you very much for inviting us. It's our pleasure to be here and present whatever that we could do in 1 hour time. Students, please keep your mind open and ask any questions. And even in between, if you have questions, you can ask, you can interrupt, or you can, like Abhishek said, put it on the chat back. So we, at the end of the talk, we can address all those questions. With that, let me get started. I thank you very much, Professor Goel. You got a pretty nice introduction about what happens at nanoscale. It's very important. That perspective is very important. So what I'm going to do is, I think, as most of you are metallurgy materials background, you all know about mechanical testing. Most of you undergraduate students, you probably have done tensile testing, compression testing in your undergraduate first year lab. So it is very, very useful to start from there. So as you know, in normal tensile testing, we measure yield strength and Young's modulus, and we take a specimen macro scale, we apply stress uniaxially and measure the yield strength and then Young's modulus. That's what we typically do. Okay, so now as Professor Goel said, that if we keep on reducing the scale or the size of this testing specimen, what will happen? You probably have read mostly from books of data that mechanical metallurgy, those students from metallurgy background, you would see that in the book that it stated yield strength is scale independent. Okay, that's what we believed 2-3 decades ago. But in reality, when you reduce the size scale, when you reduce the size of the specimen smaller and smaller, you will start to see a trend in change in mechanical property. In most of the cases, what happens is as you reduce the size of the specimens, particularly below micrometer length scale, the yield strength actually increases. This is very important to recognize, because when we study properties of materials, we often ignore the length scale effect. We cannot anymore, because at smaller length scale, the mechanical properties are different. Not only the length scale, we need to also think about the time scale. Okay, if the application requires a larger time scale or a shorter time scale, the response of the material for that time scale is also very important. So length scale as well as time scale, both are important to understand the mechanical behavior of materials. Okay, so this length scale dependency, basically we call smaller is stronger, because as you reduce the size of this specimen to smaller and smaller, you will see an increase in strength. And this has been observed around 2000, year 2000. It's been observed even before by doing defect-free materials, viscose and things like that. When you do experiments on them, you probably measure the properties closer to the theoretical strength of the materials. That is known. But in 2000, around 2002, 2003, a group of scientists at the Army Research Lab, what they did was they took samples, combustion samples, they fibbed it. You can make the samples very small when you fib it in a SEM. And they made pillars, basically, and then they started compressing those pillars. And they started to see a tendency, as you reduce the size of these pillars smaller and smaller, that yield strength basically increases as you reduce the size of the specimens. And many researchers, they repeated this experiment from micrometer length scale to nanometer length scale, and they saw a trend that you can see in this graph. As you reduce the size, the strength increases. Okay, this is something which has been observed for the last 2 decades. There are many theories why the strength of the materials increases. I'll come back to that proper explanation later with a video that will give you an idea of why the strength is increasing. But I just wanted to set the stage and just make sure that everybody understand, when you go to smaller length scale, below micron length scale, the mechanical properties are different. and most of the time the property, the mechanical property strength increases. Okay, with that, so that is the reason why we need to test materials at nanometer length scale. Okay, so what the point is, like, we have to recognize what happens to the property of the material as you reduce the size scale, uh, and if if the strength of the material increases, what causes that enhanced properties? What are the basic mechanisms? What are the roles? You know that plastic deformation in materials, in particularly metals, is mainly due to defects, dislocations, and impurities. And what is the role these dislocations and impurities at smaller length scale, like nanometer length scale? What do they play? What is their role? Okay, that's something that we need to recognize and understand. And what kind of assumptions that we have when we do material testing at macro length, which is not valid at nanometer length scale. And first, and in the lastly, I think Professor Goyal touched the point. How do we measure? Like, we are talking about 100 nanometers or below 100 nanometers length scale. How do we measure the properties of this material? Okay. So with that, actually, many years ago, when I was a PhD student in 1990s, there was a technique called nanoindentation was just coming up, and we use nanoindentation for many things. But from time of nanoindentation to now, actually, you can do mechanical testing of materials not only by indentation technique, but also like compression, tensile testing, or bending, or fracture. We can do that nowadays. Okay, in 20 years ago or 25 years ago, it was purely indentation. Anyway, so I want to connect you to the reality with a few examples. For example, like many of students are familiar with the hard disk technology. 20 years ago, when you buy a hard disk, the maximum capacity of those hard disks were about like maybe 10 gigabyte, and they're pretty expensive. Now you can buy a 1 terabyte hard disk for the same price or maybe lesser price. So the magnetic media that we use is the same. So what happened? How do the people are now able to increase the capacity of the hard disk? It's basically engineering. What they are able to do is the capacity of the hard disk, how much it can store. It depends upon the gap between the sensor that reads the magnetic bits and the magnetic media. And if the gap is smaller, you can actually store and read more data. That is what is being plotted over here. If that spacing decreases, you can have a very large increase in capacity in storing the information. Okay, so in doing so, there are some technical challenges. For example, how close you can come. For example, 20 years ago, the gap was about 30 nanometers. Okay, the spacing was about 30 nanometers. The 30 nanometer is due to the fly height, it's the air gap that you have, and the stack of materials. For example, when you have a magnetic media, you need to protect the magnetic media, and the way to protect the magnetic media is to have a diamond-like carbon coating, okay, and then some other protective coating. Similarly, for the read head, it has to be also protected because these disks are rotating about 7,200 RPM at high speed. So we need to protect the surface. So it has to be coated. So 20 years ago, it was about 30 nanometers. In today's time, those gaps are reducing about like few nanometers. Okay, and in that process, you also have to reduce the size of these coatings, the DLC coatings. That you can't have thicker coatings. The coating has to be within a nanometer or less. So now, when you have these kind of coatings, how do you go and measure the properties? You need to have some methodology. So we helped the hard disk industry right from the 20 years time scale. We have helped a lot, and that pushed our technology. We needed to go not just measure properties of that 30 nanometer thick film, which was about 20 years ago we did. Nowadays we are able to measure the properties of 1 nanometer thick film or even less. Okay. Another example that I would like to present you is Gillette shaving blade. Most of you are familiar with this, but probably you don't know. The Gillette blade is very sharp blade. It's about 25 nanometer tip radius, and it has a coating too. And this coating is about 10 nanometers or less than 10 nanometers. And in the earlier time when Gillette was trying to develop this technology, they collaborated with us to evaluate the property of this DLC coating, because we need to have this a diamond-like carbon coating to protect the steel blade underneath. Otherwise, it will become blunt pretty soon. So in the earlier days, when they sent the blades to us, we tested and we found the DLC coating was very perfect and very nice. And we told them it's pretty hard, and they realized if they can make blades like that, people don't need to buy another set of blade. They can just buy one blade and they can keep it for many years, 3 or 4 years, which is not a good thing for their business. So they engineered in a way to reduce the strength of those DLC coating in such a way that you use it maybe about 5-10 shaves and then it wears off so that they can have business. This is what they did, engineering, basically, in collaborating with us. So that's their economy, but we were able to help them to engineer that. So those coatings were about 10 nanometers or so. And another example is virus. I mean, now, because this is a very simple technique, you take a very sharp probe and put it in and measure how much penetration you can do. You can do it on any material. That's why I'm showing this example. You can also indent a virus and see what its response. And if you know the mechanical response, you can probably characterize the virus mechanically. So now, so this is another technique. Okay, now biological samples, cells, and tissues, people are using this inundation-based technique to characterize those materials and try to develop some understanding because the simplicity of the technique and the capability of the technique. So that's the reason we are in this field and trying to do whatever the best we can do in terms of instrumentation, so that the scientists and researchers can use this technology to further explore and understand. Okay. Now, with that, let me start saying what is nano-inundation. So nano-inundation, what we do is we take a very sharp probe. It's a diamond probe. And in most of the time, we use a three-sided pyramid. If you look at the corner of a cube, let's say you have a cube. If you look at the corner of the cube, it meets at one point. It's a three-sided pyramid. Right? We use something similar to that, very hard material, diamond. And then we apply by some mechanism. I'm going to talk about that a little bit later. On a sample surface, you can see that when you apply a force, you can go and make contact with the sample surface, apply a force, so that you create a dent onto the surface. Okay? And then you unload. Then you can see a small pyramidal indent on the surface. While you're doing that, you know what's the load you're applying. You also measure the displacement as you apply the load. So that gives you a load displacement curve. And from this curve, you can go and decode all the other mechanical properties, elastic properties and plastic properties, both modulus and hardness of the material. Okay, that is what has been done in a simple nano-inundation experiment. So how do we do that? How do we generate the force? It's a very simple concept. We use electrostatic force actuation. A simple example that I give is basically if you take a comb, I think you probably have done in your childhood days, you just rub it on your head, you create a high voltage on the comb, and you bring it closer to a small paper, and the paper jumps to the comb because of the electrostatic force, force of attraction. We use the same concept. So you have this three-plate capacitance structure. The center plate is supported by a spring so that it can move up and down. And these gaps are very small. I mean, the gap that we have between these three plates, the gap is about like it's 50 to 60 micron. Okay. And now, if you apply a high voltage at the bottom plate, it will generate the electrostatic force, and this center plate will get attracted to the bottom plate. That is how you generate the force. Now, if you put a tip into the center plate, and then the tip is being in contact with the specimen, then you can apply the force onto the sample and measure the displacement. To measure the displacement, what we do is we measure the capacitance between these parallel plates. You know that when you have a parallel plate and because of the air gap, there is a capacitance. So when the center plate moves in between these two outer plates, the gap is changing. Because the gap is changing, the capacitance is going to change. And if you have a way of measuring the change in capacitance, you can measure the displacement. So with this simple concept, we can apply force and measure displacement. So this is what we use. It's a very simple concept, and it's all precisely manufactured transducer. And in this equation, if you look at, if I apply a voltage, and the force generated is proportional to a voltage square, and it is proportional to a constant. It's as simple as that. So as long as I know the voltage that I apply, I can calculate the force. Similarly, for the displacement, it's a change in capacitance. You can measure the change in capacitance in terms of voltage, and then you can convert that into a displacement. So this is a very simple way of applying the force and measuring the displacement. Now, if you mount this transducer on a 3-axis piezo positioner, this is a piezo material, and the materials to science students, you know that if you apply a voltage to a piezo material, you can generate a mechanical action, mechanical force. So we use that concept to move the piezo in X and as well as Y direction, as well as in Z direction. Okay, so you can use it as a scanner, and that is a technique being used in the AFM, and we use a similar technique. Is a tube piezo scanner, and then you can mount the transducer on the piezo scanner, so that you can move this transducer in 3-dimensional space in X direction, as well as Y direction, as well as in Z directions. So in that way, we can move tens of microns, like about 50, 60 microns or 80 microns in X and Y, and about 10 microns in the Z axis. So now this transducer is mounted on this 3D piezo scanner, and we can scan this transducer. Now let's say the tip is in contact with the sample surface, and when you scan with the piezo, the tip is sliding on the surface, and because the spring stiffness is so low, then because of the surface roughness, the tip will move up and down like a profilometer. Okay. Now we can regard this change in, you can regard this profile of what the surface, and you can construct with this profile the 3D map of the surface. That is how we can go and see what is on the surface. That's what I'm showing in this particular slide. Okay. So there are a couple of images that you can see. The first image that you see is basically a wood cell, and you can see the cell wall around the cell, and you can see tiny indents around the cell wall. Okay. So with this transducer and the scanner, we were able to go and scan on the surface, create this image. Now this image is about like 20 to 20 micron, and sometimes you can create images less than a micron. So you have the ability to see what is on the surface, kind of a microscopy, which has a better resolution than optical microscopy. Almost closer to the scanning electron microscope, you can go and see the surface with high resolution. And within this image, you can see where we wanted to go and do this indentation experiment. We can pinpoint within plus or minus 10 nanometer position accuracy. You can go and pinpoint the location where you want to do the indent. Let's say when I want to select this particular space, a particular point, you can go select and do an indent. Okay, that's what we call in-situ scanning nano indenter, because we can generate this surface maps in situ. Okay. Now, with that capability, that we can go image the surface and have an idea of what we can look at how we can look at the surface, and we can pinpointly select a location where you want to do the test, and do a test like by doing indentation experiment and creating this low displacement curve. From the low displacement curve, we can measure hardness and modulus. The theory behind this is very simple. You are taking a probe and you know the shape of this probe. I said 3-sided pyramidal probe, but the tip end is something that you don't know what the shape is. It's normally spherical. But by doing calibration on a known sample, for example, if you take a fused quartz sample for which the modulus of the material is known, and you do an indent and you measure the stiffness is measured from the unloading curve of the load displacement curve. You load and unload, this is the typical load displacement curve. And from the unloading curve, this is the load, this is the displacement. If you take a slope, it's basically stiffness, right? So you measure the stiffness from this unloading curve. And once you know the stiffness, in this equation, you can see, you can calculate the modulus. For example, if you have a material for which you know the modulus by some other technique, X-ray or sound or something, you know, if, for example, fused quartz modulus is known, so I know what the modulus of the material is, and I can do an indent experiment and measure the stiffness of the contact at a given load. And for a load, for a given penetration depth, I know the geometry, and from the geometry, I can approximately calculate what the contact size is. But in our case, I know what the force I applied, I know what the stiffness is, and I know what the modulus is. I can compute the contact size, which is in this case is basically area that I've shown here in a shaded color for a given depth. So in that way, we can calibrate the tip for a given depth. What is the calculated area? So then we can go and take the same tip, which is basically a diamond tip, and indent on some other material for which you don't know the modulus, but we know for a given depth what is the contact area is. From that calibration curve, you can, if you know what the stiffness is, you can go calculate the modulus of the material. Okay, this is how we measure the modulus of the material. And if you take the load divided by area, gives you the hardness. And this is how we measure the hardness and modulus of the material. It's as simple as that. Okay. So now this load displacement curve, they are unique. Most of your material science students, you know that when you do a tensile test, the tensile test, the curve is depending upon the material that you use. Similar to that, here also the load displacement curve that you get with this indentation experiment depends upon the structure of the material. So sometimes the material may be highly elastic, sometimes highly plastic, depending upon the material. So we call this is kind of a fingerprint of the material, mechanical fingerprint of the material. For example, if you do it on a fused quartz, you will have a response something like that. You have a elastoplastic deformation, and then when you unload, there is some kind of a recovery. Whereas when you do the same experiment on aluminum, you don't see much of a recovery. It's highly plastic. So there is a difference between the load displacement curve between the fused quartz as well as aluminum. And also, like for example, if you do it on a polymer, it will look totally different for a given load. Same thing, you can also do it on biological materials, soft materials, like in this case this is a tooth. So the load displacement curve that you get, it depends upon the material, and it depends on the structure of the material. Okay. So in that way, we can have a structure property correlation directly by doing this experiment and getting this load displacement curve. Okay. So now we can extend this to, for example, if you are interested in tribology, you can do that by adding another transducer on the lateral side and sliding the transducer and applying the normal load and doing a scratch test. Okay. At the same time, you can now you can apply a normal load. You can measure the normal displacement. Along with that, you can also apply lateral force and measure the lateral displacement. And you can also, from the normal force and the lateral force, you can calculate the coefficient of friction. And if you do that on a material, for example, if you have a thin film coating on a substrate, and if you wanted to measure the adhesion center of this coating, you can use this kind of techniques where you can progressively increase the normal load. And at some point, the material will delaminate from the surface, and you can measure what is the critical load that required to delaminate the material from, and this equation, you can go and measure the adhesion strength between this coating and the substrate. You can do that, okay? And into the next step, if you wanted to understand the wear properties of this material, while you do the imaging, you can progressively increase the load, and you can wear the material and then and there. For example, if you have a multi-phase material, and you want to know wear property of one phase with respect to other, you can go and wear that particular phase. And you can, because we have the imaging capability, you can go and calculate what is the wear volume directly from the image. In that way, you can also extend to understand the tribological characteristic of the material. Okay. Again, like because we have the imaging capability, you can do indent on ceramic material. When you do indent on a ceramic material with the type, I mean, we call this corner cube indenter tip, which has a higher strain, you generate this crack, and you can go measure this crack length through this image. And you know the Young's modulus, you know the hardness in the same indentation experiment. With all these parameters, you can go and even calculate the fracture toughness. It's not very quantitative as your regular fracture toughness measurement, but for ceramic material, if you have the crack length, which is much longer than the width of this indent, it does work. Okay, so in that process, you can calculate the fracture toughness of this material. Okay, now I'm keep on adding what all things you can do with this simple experiment of indentation. Not only measuring hardness and modulus, I have given some example that you can go and do tribological characteristic. You can measure with the lateral transducer, you can measure the lateral force, you can measure the friction force, you can do crash testing and measure the adhesion strength, and you can also extend it to fracture mechanics. For example, you can go and measure the fracture toughness of the material. Okay. Now I'm going to go and use it for on polymer materials. Okay. Instead of applying a static force like quasi-static force and measuring the load displacement response, I can also superimpose a dynamic force, a sinusoidal force, and measure the sinusoidal displacement response. For example, if I apply a sinusoidal force and use a locking technique, basically if I apply a sinusoidal force at a given frequency, and I only look for the response at the same frequency, the displacement response, and I can measure this the displacement amplitude, and I know what the force amplitude applied. If I take the force amplitude by displacement amplitude, it will give me directly what's the stiffness of this contact. And from that, and if I do it on a polymer material, I can directly go understand the storage and loss component of this viscoelastic polymer materials. What I mean here is basically, let's say when you apply a sinusoidal force, which is basically is this red curve, sinusoidal curve, and then if you measure the displacement response, and that is the blue curve, if there is no phase shift, for example, when you do it on a typical metals, you won't see any phase shift. They will be, the force and the displacement will be totally overlap with each other. There won't be any phase shift. But if you do it on a viscoelastic material like polymers, you will see this phase shift. Actually, the displacement will lag behind the force. And when you apply a force, it takes a little bit time for the material to respond. So the displacement will lag behind the force. And if you measure this phase lag, you can calculate the loss component of this viscoelastic material. So we call storage and loss modulus. We can also do that using this technique. We call it nanodynamic measurement technique. Okay. Now, if you have a way of applying now heating the sample, let's, for example, you can with this transducer technology, with this scanning technology, we can indent, we can image. But now, let's say if you wanted to change the temperature of the specimen, then we can do the experiments as a function of temperature. So we also developed a heating stage. I'm just going to give you one slide overview of the heating stage. It's basically a two-part stage. Basically, there is a top part, which is also a heater, bottom part, which is also a heater. So you put the sample in between these two heaters and sandwich the sample so that you heat the sample from the top as well as from the bottom. And in this construction, we design it in a way the thermal expansion of one is cancels the others. So the net thermal expansion in the Z direction is only 6 nanometers per degree C. With that, we were able to have a nanometer length scale stability. At the same time, we can go temperature as high as 1000 degrees C, as cold as minus 120 degrees C, so that we were able to change the temperature from cryogenic to very high temperature up to 1000 and still be able to study the nanomechanical properties of material and its response at different temperature. Okay, I'm going to go show a few examples here. This is a polycarbonate, and I mentioned the dynamic measuring capability, like you apply a sinusoidal force and measure the sinusoidal displacement response and measure the stiffness, the storage component as well as the loss component. From the stiffness, you calculate what the storage modulus and loss modulus. That is what is plotted over here as a function of temperature. You can see the storage modulus at glass transition temperature. You can see this drop, and also the loss modulus. You can see a peak during the glass transition temperature, and you can do that as a function of temperature as well as a function of frequency. That we call it superimposition. Basically, we can measure what temperature and what frequency the material properties are almost the same. We can figure that out. Okay, so this is very useful for polymer materials, and you can also go and measure the tan delta. This is for polymer thin film. I'm talking about these films are, hello?
Dr. Sayed, Dr. Goyal. So how much is the load? What is the load in case of nano DMA? Maximum load and minimum load?
Minimum load, we can go like few micronewton, sometimes even like tens of nanometers, 30, 40, 50 nanometers minimum load. Maximum load is 10 millinewton.
Okay, thank you.
So we can do that, and then We can also measure the tan delta. Tan delta is basically the ratio between the storage and the loss modulus, and you can measure as a function of temperature. You can go at lower temperature as well as higher temperature. So it's useful for polymer material characterization as well. So this simple concept of doing with a probe and the transducer, applying a force onto the sample and having a probe of different type of probe, like pyramidal probe or a spherical probe, you can change the configuration, and then by applying the sinusoidal force, I mean, you can do so many things with this same setup. That's why these techniques are becoming very powerful. Okay. Now, instead of measuring at one location, like I mentioned that imaging, you can also scan on the surface as you do this modulation. I mentioned that you have to oscillate the force and measure the displacement response. You do that as you image the surface, right? You can measure the stiffness as a function of position, and with that, you can create maps, okay? For example, in this is a property map. You do the modulation and then scan on the surface. And this is for a fiber epoxy composite. And with that map, you can go and measure the storage and loss modulus as an image. This is a fiber epoxy composite. You can see the fiber has a different modulus compared to the epoxy here outside. And you can do that storage as well as loss modulus. So instead of measuring the modulus at one point and then neighboring points, in this case, basically it is almost 256 by 256 points, which means that if you want to do that many indents, it will probably take about 30 days, but we can do this imaging within like 5 to 10 minutes. So now you have a high throughput of data. You can measure, you can go and image the property as an image, and that is very useful. Okay. So we also have another technique where we can go and do an indent. In the previous case, you just measure the modulus, but you don't measure the hardness because the depth, we are still within the elastic contact. But if you want to measure the hardness, which is basically a plastic deformation, you do an indent, and you can do those indents very fast. For example, you can do 5 indents per second, and within like 20 by 400 indents, you can do it in 80 seconds. And along with this, the heating stage that I've shown before, you can do this at 400 degree, 800 degree, even up to 1000 degrees C. So you can do a property map pretty fast using this technique, and then you can go on the hardness. You can measure the hardness as well as modulus. Both the maps you can do that. Okay. So not only modulus, we can also do a hardness with this technique. Okay. So there are many examples, and the material, you can have a wide variety of materials. I've shown pictures of wood cell indentation, and people have even somehow like they were able to anchor a red blood cell, and they were able to image the red blood cell using this technique. So it opens up a spectrum of materials, from ceramics to very soft materials, biological materials, polymers, metals, even devices. If you wanted to measure the stiffness of these MEMS devices, you can do that. If you want to evaluate how much actuation force they create, you can do that. So it is kind of unlimited. It only up to your imagination how you want to use this instrument, because it has the capability to apply force in a controlled manner, measure displacement in a controlled manner. You can put any type of probe and then enhance your understanding. Okay. So it has been used on many industries. I've just listed 15 of those, and most of these industries are now using this kind of technique in R&D at even production level. Semiconductor industry uses our technique all the time to characterize the semiconductor wafers, and similarly aerospace, automobile industry, most of these industries are moving with this kind of technology now. Okay. Now, so in 20 years development, we have done a lot of work, and most of this has gone to a different domains. I'll be later going to present In-Situ nanomechanics with basically whatever that I presented can be done inside an electron microscope. I'm going to present a few results on that. And also I mentioned that we've used this technology in semiconductor fab lab. This is the instrument, the big instrument is a multi-million-dollar instrument that sits in the line and characterize the wafer using this technology. Okay. So I also wanted to take this opportunity and introduce a system that we developed in India by Induston in India. and it basically it measures the nanomechanical property that I just presented here, and it is basically a desktop system. And our original intention was that we need to have this system that is we can put it on a desktop in a classroom where we can directly go and use this instrument to teach the fundamental material science mechanics with this instrument. That was our intention, and you can also use it for research and other purposes. So this has been manufactured in India and in Iran. We developed and manufactured this instrument in India. Okay, and then now I wanted to move to a different direction. I mentioned all these things up till now that experiments been done outside. I mean, it's a standalone instrument and in atmospheric conditions. Now we figured out a way to put this instrument inside an electron microscope, and the reason behind is basically to understand their fundamental mechanics. For example, in the beginning, I said I will come back to you why the strength increases as you reduce the size. I'm going to go show this particular video that will give you an idea. This is a pillar, and similar to the pillars that this is around the same time scale when a group of people were started working on that and then reporting that there is an increase in strength as you reduce the size, and we wanted to know why. So at that time, we were developing this instrumentation inside a transmission electron microscope. This particular experiment was done inside a transmission electron microscope. You can see the pillar over here, and underneath you see a flat indented tip. I'm going to go, this material is being prepared by fibbing technique. Okay, this is a field ion basically use and you kind of carve the pillar out. When you do that, you create defects, and these defects are the dark things that you can see on this pillar. Okay, those are all dislocations that is been created when you carve this pillar. Now go in compress it, you can see that kind of a marvelous thing that happens. Okay, and when you compress, all the dislocations that were there in the pillar, they disappear, and that pillar become totally dislocation free. This is something against like what we talk about annealing and work hardening. For example, in this mechanical deformation, if there are dislocations, when you apply a stress, it should create more dislocations. But in this case, you can see that all those dislocations that generated were moving to the surface, and they disappear to the surface, and that makes the pillar dislocation free. As you know that when the material is dislocation free, it will almost go to the theoretical strength of the material. That's the strength increases. This is because the starvation of the dislocation. What is really happening is, for a dislocation to multiply, we know that it has to move a characteristic length. It has to move a distance. Okay. Now the pillar is so small, and that characteristic length is much bigger than this pillar size. So before it moves and creates another dislocation, actually it disappears at the surface. That's why all the dislocations are moving to the surface and they disappear. And the material is less of a dislocation that gives you the strength. This is one of the explanations that we came up with this, doing experiment inside a transparent electron microscope. Another thing, there were a lot of ambiguity in understanding. Like, for example, when you do indentation experiments, sometimes you see a jump in the low displacement curve, and these jumps being attributed to sudden nucleation of dislocation. For example, you have a defect-free surface. When you do it in a nanometer length scale, you're talking about statistic. Okay, beneath the indenter, the number of dislocation may be very small when you do the indent, and by applying the stress, you may be nucleating more dislocations. And as the dislocation multiply, you see a sudden jump. That is what is being proposed. We wanted to confirm that, so we did this experiment inside the TEM with this TEM nano indenter. This is the indenter tip. This is an aluminum grind, and you can have a two-beam condition in a way that we can find grinds without any dislocation. You can see it's a dislocation free. Now, when I do the indent, you can see as soon as it touches, it pops nucleation of dislocation. These sudden things that you see, that dark, these are all like dislocation. Okay, and correspondingly, you see the jumps in this low displacement curve. From this low displacement curve, as well as from the image, we can calculate what are the stresses. We found the stress at the point when it nucleates dislocations almost to the theoretical strength of the material. So we gave a direct proof of what we believe, that whatever the jumps that you see on this kind of material is due to dislocation, nucleation, and multiplication. This was done like in 2006. Many years ago. So now we can use these tools inside the SEM or a TEM and then applying the load and measuring the displacement, you can calculate the stresses that you are applying, and you can see directly what is going on within the specimen, and you can have a direct correlation. You don't need to make any assumption. You can see, and then you can believe what's going on. So that is the power of this kind of technique. So this is something that I wanted to give as we did very recently. This is an experiment that we did on silicon, and this is done as a function of temperature. And normally when you increase the temperature of the material, you should see a decrease in strength, and that's because mobility increases and dislocation can move easily. That's what you expect. The hardness or the yield strength will decrease as a function of a high increasing temperature. In silicon, what happens is it's kind of a little bit mystery. The hardness initially increases up to 200 degrees C and then decreases. This is mainly because there are two things happens. In silicon, when you indent, there is a stress-induced phase transformation, and also like higher temperature, you have slip-based deformation, plastic deformation. So there are two competing mechanisms, and because of that, you see a peak, and then the hardness decreases. So with that, we were trying to understand more on silicon. Particularly, it is also very important electronic material. So we wanted to understand like mostly the manipulation of the material, basically in silicon. When you bring a very sharp probe or when you make contact, what happens to silicon. So we did a very interesting experiment inside a TEM, and this is very, very low forces, is about 10, 15 micronewton force. And you can see the high resolution TEM image here. The dots are all kind of representative positions of the silicon atoms. And this is the diamond probe. This is silicon, and you can see to the level that we can do nowadays, atomic scale, you can do these experiments, and then you can apply this stress in a controllable way, and you can start to observe. For example, you can see the stacking fault here, and I will go through this slide. And then all this perturbation that you see on the low displacement, it is mainly due to, it's not noise, basically, it means something. There are defects created, you create vacancies, and stacking faults and all the other things as you do the deformation. And this is kind of atomic resolution image, and we can get the low displacement response. Now, if you go look at, you can see when you bring the tip and make contact, initially you see this amorphous phase. We never expected that you will have an amorphous phase first, and then you can see stacking fault before that sample, and after when you do the indent, how the stacking fault is growing, line defects, lattice rotation, folder lattice. So we can do pretty much, you can see atomic scale defects. I can correlate that with the low displacement curve. Okay, we need to develop much more understanding, but we have the tools which allows us to go to atomic scale and make observation and make some measurement. Okay. Now, same thing, like we can do tensile test experiments. This is a copper film. It's also done inside a transmission electron microscope, and you can record that. And then this is an experiment done inside a scanning electron microscope. This is a silica particle being compressed. I'm going to show the video. It's a compression of that, and then you can do a fatigue test on the silicon, this silica particle. This particle is about 1 micron in size, and you can see how much plasticity it goes through. Pretty much with we found that with the electron beam, we can go have a very high, we can deform this material to up to very high strain, and you can do fatigue test. Okay. So not only that, we can also do kind of a tribology test inside the TEM, and we can do it in SEM as well. And maybe I will play this video as well. You can see as you slide on the surface, you start to pop more dislocations. You can see the bands of dislocation that happen and that forms. And by repeating, you can see the material getting removed. And at the same time, you can measure both the lateral as well as normal force. And you can do that pretty nicely. So we started understanding the tribological characteristic. This is something that has been very eluding for tribologists. What happens when you slide beneath the sample? We now have a tool that we can go understand that. Okay. Now this is also this is an example with the SEM, and you can see there is a scratch done with the normal load progressively increasing the normal load as you scratch. At some point, you can see the material will come off from the surface, and you can calculate what is the load. So you saw the crack formation. You can see that load drop here in the load displacement curve, and the material got removed. You saw the big load drop. And with this image that you see on the SEM and on the force and the displacement you have, you can have a direct correlation of what is going on, what type of deformation, what type of delamination happens with the material, and what is the corresponding stress. We can do that. Okay, that's an example. Okay, so we can do so many other type of tests. For example, I've given 2 or 3 here, where you have a weird spring here. We are deforming that. Here, this is a stock of material for electronic packaging. We're doing the 3-point bend test over here, and then you can see that at some point it's going to fracture, and it's the fracture load. And this is a compression experiment done at a higher temperature. You can see the serrated flow. So these are all done inside the SEM. And nowadays we can do this, and we can observe what's happening to the material directly and measure the load displacement curve. And from that, you can calculate the stresses. So that I'm going to go stop, and I think it's almost my time. And then I'll take any questions if the students have before we go to the demo part of the talk. Okay.
So, Dr. Syed, really, I must appreciate this talk. Actually, this is the first time I have listened. So interesting and means you can say practical talk in my life of 25 to 30 years of experience. Actually, really, I must appreciate this talk. And I think all students must have enjoyed this, and many senior faculty members are also attending this lecture. So first, I will give opportunity to them, then later on I will ask question.
Definitely, yeah. Please.
Thank you, Dr. Asif, for this very insightful and informative talk. I really enjoyed your talk, and I hope all our students and all the faculty members who are joining us and research scholars have also enjoyed your talk very much. So thanks a lot. So there are some questions which we have received from the chat box. So Mr. Yatharth is asking, what kind of indenters do we use for nano indentation? Only diamond indenter or anything else?
Most of the time we use diamond because it's pretty hard and rigid. We don't want the indenter to deform when you do the indent. Because at the apex of the indent, you have a very high stress. So you need to have something very rigid. So, but when you indent on soft materials, we can use other materials. So biological samples, we don't need to use diamond. We use sometimes steel, sometimes carbides. And high temperature experiments, for example, when you do it on a carbon steel, if you indent with a diamond at a higher temperature, because of the reaction, you will lose the diamond tape. In those cases, we use sapphire or some other carbide. So depending upon application, you can have different type of tips. That answers the question. Okay.
So we have another question from Mr. Naveen. So he's asking, can silicon carbide be used instead of diamond as an indenter?
Yeah, you can use silicon carbide, but you can use it maybe even soft metals, but I won't recommend for other materials, because as you indent, if the indent tip is deforming, you don't know the shape of the indent. Okay, so if you use metals and hard materials and ceramics, I recommend diamond. But if you use soft materials, soft metals, it's okay to use silicon carbide. Okay.
We have another question from Rishika. She's asking, what is the size of samples for tensile testing and how to prepare them?
You are talking about nanotensile test, right? These samples are like, you need to fib them in an SEM. And you can do maybe micro iridium, but I don't, or you can etch them by photolithography. That's all the 3 processes that I can think of to make samples. These samples are very small. They are like microns, a few microns to nanometers scale size. Okay, and making them is a difficult thing. So most of the people who have a SEM with a fib, they prepare all the samples by fibbing. Okay.
I have one question, Dr. Said. I was really impressed to see the in situ TEM experiments. Uh, so how exactly is it done? Like, do you? So we have these thin samples.
Mhm.
So what kind of like in which direction do you apply force? Like, is it
Well,
along the thickness or perpendicular to the thickness?
it depends. For example, the experiment that I've shown you, that aluminum grain experiment, in that experiment, what we did was we did the deposition of aluminum on a wedge. Okay. So at the sharp apex of the wedge, the material is transparent. Okay. Now you are indenting perpendicular to that wedge, and the electron beam is passing through the thickness of the sample, and it is electron transparent. That's how we are able to do that. So normally with indentation, that's what we do. Okay, I don't know that I don't have a. So this is basically the material is on a wedge. Okay, and and then the electron beam is passing through the wedge, and then you're indenting perpendicular to the wedge. And here basically with the silicon, this is a cylindrical sample, and this is electron transparent. Again, it is only 50 nanometers, maybe about 100 nanometers, still electron transparent. So we can apply the flat tape, we can compress it, and perpendicular to this cylinder, and the electron beam is passing through the thickness of the material. Yeah.
Mm-hmm. One point which comes to my mind is that when we do all these mechanical testing at very small length scales,
Mm-hmm.
but in our actual real life applications, we have all these bulk samples.
Mm-hmm.
So how the properties which we achieve at the very small scale is useful for us when we are using this material in our real life applications.
Well, the mechanism, the underlying mechanism, it has to start with the microstructure, right? So if the microstructure if we have is basically a nanometer length scale, if the grains are smaller in nano size, and that definitely it's going to change the property of the bulk also, right? That's one thing. The second thing is, for example, I've shown video where the theoretical strength of the material that you can measure by doing at a small indent depth, and it gives me an idea what kind of a mechanisms happens basically. Okay, and that kind of a mechanism I can explore with the nanoscale, and basically to understand the fundamental deformation mechanics. Okay, you may, for example, like if I say yeah, the tungsten creeps at room temperature, you may not believe it, but I can measure that with nanoscale experiments. I can see the creep. Okay, with
Mhm.
bulk experiment, you won't be able to measure that because these creeps are basically maybe less than 0.05 nanometers per second. And if you have a sensor or a transducer which is capable of measuring that, only you can see. Okay, so in sometime experiments, like for example, when you bring two specimen and make slight in contact, elastic contact, because of the stress at the interface, you have a chemical potential difference gradient that promotes the diffusion of atoms from underneath the sample surface to the top of the surface. And
Mhm.
now this, if it is measurable that you can do with this transducer, you can see that. Otherwise, you will say that it's just an elastic contact. So you won't be able to even understand. Okay, but there is something happening. There is a diffusion of atoms. Okay, so now it enhances your understanding what is happening in the material. Only when you see the result, you can go and model. You try to build up this understanding. Okay, the same thing that I've shown on the silicon. When you make contact, there is a number of phase. We never thought like the. We always thought on silicon there is a stress-induced transformation from semiconductor to metallic state. We never thought about amorphous phase formation at the surface. Only when we see, oh, there is an amorphous phase forming. Okay, why it can be? Now people have started thinking about what's maybe when you bring a diamond to the silicon, what's happening at the interface. So it is kind of making our thought process to go wild and try to accommodate more in our thinking and in modeling and all those things. So it's fundamentally changing our perspective of what we believe as material behavior, right? That is what is happening. That is why you need to do it at smaller length scale.
Mhm.
Okay,
That's correct.
so that is what is going to kind of give you an idea why most of the bulk behavior we already know, but there are certain things we don't know yet. Right? We are
Mhm.
trying to figure those things out. So that is the reason. Okay.
Yeah, thank you. Thank you. Um, we have another question from Rasdeep Bhattacharya. So he's asking, since we are dealing in nanoscale, are there any visible variation to the results of the test performed? And if yes, how do we optimize such variations?
Well, always there will be a statistic, right? Everything is statistic. So you need to do number of tests and then you can use the statistic to kind of guide you. Because properties of the materials, when you try to measure, most of the time, if you, let's say, for example, if you take fused quartz, if you try to measure the hardness, most of the time you probably measure about 8.3, 8.4, about 9 GPa. We know that it's kind of the measure, hardness that you're supposed to measure. And when we do repeated indent on fused quartz, for example, in the whole surface area, you do 100 indents, and then you put all the curves together, they overlap pretty much 100%. Okay, you may see little changes like in 1 nanometer to nanometer. So which says that the material is homogeneous. That's why we use fused quartz as a standard sample, the sample that we supply. But if you do it on a copper or other material, the defect densities may be different. It's I don't know. Like it all depends upon where you indent. So it may be site specific. So there will be variation. But what you do is you do a number of tests, more number of tests. So you have a statistic to guide you to give an idea what's going on. Okay, that's why you need to do a lot of tests. Okay.
Yeah. And sometime, Professor Dr. Said, it may also, I think, hopefully depend on how you prepare your samples.
Samples too.
So,
That's true. Yeah, yeah. It's also depends on sample preparation.
And
So yeah,
distribution.
yep, that's true.
Professor, you are saying something?
I am saying distribution of the grain size also, because
Yeah,
there
yeah,
will
yeah, yeah,
be from grain size of the materials, so there may be
yeah,
variation, then defects. Second
yep,
thing, the idea of having the means properties of the nanomaterials may be helpful for the bulk nanostructured materials.
yep,
That is more useful.
yeah, yeah, yeah. That's true.
I think Professor Bhargava is also online, sir. You are having very good experience in mechanical testing. So if you have any question, please, so that if you ask,
Please.
then you will also learn. Professor Bhargava? Okay, so I think anyway, so
Uh, we have some more questions in the chat box.
okay.
Okay.
Himanshu is asking, as we could see the dislocation disappeared, where exactly do they disappear to? Do they
It,
accumulate on the surface or they get vanished completely? I
now
think that
it
was,
goes to the
yeah.
surface. It creates a step. Okay. The dislocation when they disappear on the surface, it will create a step, a burger, whatever that. Okay.
Um, Dr. Swati Sharma is asking, is there any empirical relationship that holds good for nano-sized particles, like we have Hall-Patch relationship, but that is not valid in nano-length scale?
Oh, I am sorry. I don't know much about that. I know, but for particle, I don't understand the question, and I don't think I have an answer for now. I have, with respect to particle size, I don't know. There may be some relationship, which I'm not aware of that.
Sayed, partially I can answer this question. So what she is asking, when we reduce the grain size of the
Yep.
metal fluid, what happens in the beginning?
Mm-hmm.
Strength hardness will increase, but below the grain size of about, you can say 50 to 60 nanometer, when we
Mm-hmm.
reduce the grain size further, means to 40, 30, 20 nanometer, then
Mm-hmm.
strength or hardness is reduced instead of decreased.
Reverse Hall patch. Yeah, reverse
Yes,
Hall
that
patch.
is known as
Yeah,
reverse with relationship. But that
yeah,
is
yeah,
very, and many researchers have done this, that is study, and it is true. So up to the critical size, we will get increasing in the hardness, but
yeah,
below particular sizes, we will get the decrease in the hardness. That is because of the global creep phenomena.
yeah.
Yes, sir. Actually, this is what my question is. And the thing is that once we go on decreasing the size, definitely this Hall pitch relationship does not hold good over there.
Mm-hmm.
So, is there any mathematical model that is being developed? Like you are working on the instruments, so
Yeah. So
yeah.
I know about Hall patch and reverse Hall patch, but other than that, I have. There must be. I'm not. I'm not an expert on that, so I don't know the answer for that. There must be some relationship people have found, but I haven't followed for some time now.
Yeah, sure,
Yeah.
sir.
Yeah.
Swati,
Okay.
Actually, some authors have given the formula means instead of inversely proportional means directly proportional below that size, below the
Yeah,
critical.
yeah,
So
Yeah, maybe that is what, but how does that correlate? That is what I was just
yeah.
wondering that if people have worked on this.
I know there are a lot of people working on this, especially I know there are a lot of people are working on that. But I think I've heard about Hall pitch and then reverse Hall pitch, but beyond that, haven't seen any mathematical. I'm not aware of that, so it may
Okay,
be there.
no problem,
Okay.
sir.
Dr.
Yeah.
Sayed,
Yeah.
see, maybe we may have another meeting after maybe whenever you have time. But anyway, so before all the participants, I can ask one question. How much is the
Yeah.
cost of nano DMA for the basic
Uh,
unit?
it depends upon the instrument. Pratyang will be the right person to ask that question in a separate meeting.
Cost. I am asking tentative. Later on, we can have means our
Yeah,
council.
yeah, 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 yeah. I think
We can,
Pratyang should be able to answer that.
Yeah,
Yeah,
I mean, is it from Professor Goel? Is it?
yes,
yeah.
yeah.
Yeah. So that can go from you can see if you want DMA system, we are looking at around 120K or so
120K.
USD.
Acha. 120. Hmm.
Yeah, but that will give you a lot of other features also along with DMA. Like Dr. Asif was talk about structure property correlation. You can do imaging and then you can correlate
Yeah,
these
it's
properties.
not just DMA, it is indentation plus DMA, all of that.
Indentation, SPM imaging, nanoware, DMA, and then accelerated property mapping. So
Yeah.
you get complete as a package which can serve or suffice your research requirements in all aspects.
So means you are saying means 120K means 1000. Sorry,
I mean, in
100
INR, if you multiply 73, so it's yeah, close to let's say 90 lakh or so, maybe. Yeah.
Yep.
90 lakhs. Okay. So
No,
anyway,
but
mm,
okay.
yeah. For academic institute, and we need not to pay custom duty because, and I think it is not in India. No, we need to import.
Yeah.
See,
We
yeah,
have a variety of systems, so depending
yeah.
upon the system, the price vary. Okay.
So
See, Dr. Asif is going to also give a demo, Dr. Goel, on the instrument that we developed in India,
In India, that's
which
a
is
different
all,
instrument.
yeah. So
that
that
nano
can
group,
do, sorry,
that is nano group.
nano
Nano
group.
Guru. Yeah, yeah, yeah.
But that also has a similar capability. I mean, DMA is still under, I could say development,
Development.
but
Yeah.
yeah, but that system now we are based on our academic requirements. We're putting around 50, 50 lakh, but that can also give you indentation, SPM imaging, nanoware.
Okay.
So the features like I say accelerated property mapping, that's you can say 6 months or 8 months down the line.
Means so far,
Or
have you tried this nano group to any academic institute or organization in India?
we have kind of collaborated with like Indian Institute of Science, and recently we had a session with IIT Delhi, where they included this in part of their teaching.
Okay.
So it's a we got this concept earlier, but we are more aggressive only for last
It's
year.
more of a work in progress in India.
Okay.
Yeah. Since 2020, we are more aggressively working in this direction, and based on the seeing how the government
Yeah.
the new rules that are coming up, we feel this is the best way to go for and developing things in India now.
Yeah. Very interesting. So actually today's lecture is very interesting actually. Anyway, so I thought that it will be towards or discussion maybe towards means non-technical you can say, but or towards marketing side. But
No, no.
We
So
don't do that.
actually,
We don't do
no,
that.
we don't do. You can see
We don't
all
do
our
that.
events
Yeah,
that we do.
we are researchers. We do hardcore research. Basically, we work with universities and professors. We collaborate. We did all the institute. What you saw, it's all our own work in collaboration with other institutions, professors, IISc. We are very good. We have been doing a very long term collaboration with IISc. So
Also
yeah,
with in IIT Bombay with Professor Samajda, we had a brief collaboration. Then with Professor
yeah,
Preetapand in IIT
yeah.
Bombay.
Yeah.
So other reputed institutes like in India, we are always open for it, basically.
We can
Yeah.
also have collaboration because our UG and PG students are very hardworking, sincere, and
Yeah.
honest in working. So we can
Yeah.
think on that also.
Yeah. Yeah, but if you see the system that Dr. As is going to show, it's, as I say, based on our current funding, and this is the
Yeah.
best, suited system for the current environment.
Yeah. That's true. So I think
On the side,
maybe it's
I will
time.
maybe yeah, I think I would maybe propose to maybe we can start the demonstration.
Yeah. Yeah.
Then
Yeah. So yeah, yeah, everybody can see my screen,
We
the
can
Nano
see.
Guru.
Yeah, yeah, yeah,
You can see that, right? Okay. So then I will start that. Just a
yeah.
minute.
That's the software screen, right, Dr. As? Yeah.
Yeah. Yeah. Yeah. Yeah. Yeah. So this is the Nano Guru system. That what you see is the in the image. That this is the interface that we use. And this is a pre-recorded one, so that then it is easy for me to go through. And when you start the nanoguru package, basically software package, this is the interface that you will see. And if anybody has used Hydrogen system, they will see a big difference between that and this. The reason why we built this way is very, very easy to use. You will see that in a few minutes. So you can see there are 3 counters here. The top 3 counters kind of gives you an indication of sample force, and you can see, okay, and then the sample force and the actuation force and the displacement of the transducer. So it kind of gives you a feedback of what is happening with the system, so that we keep an eye on these readings. Okay. And then so this is the software interface which controls the nanoguru system. Okay, so let me, okay. So the second one is, if you look at this interface, there are menus laid out in a way that it will be very useful for people. The way it is been laid out is basically how you wanted to progress in your workflow. So it starts with about, it gives you all the information about the instrument, and then it goes to the system constants. System constant is basically the calibration constant of the transducer and the scanner. And we calibrate the transducer and the scanner at the factory using laser interferometer. When you do that, when you look at this calibration value, you can see that. Okay, so this gives you kind of a values. This is a load scale factor. Basically, it's kind of a force calibration. This is the displacement scale factor, basically a displacement calibration. This is the electrostatic force that I mentioned in my talk, that when you apply a voltage, you generate the electrostatic force. This is that constant that in front of that equation. This is the constant that you need to have. So with this, all this is being calibrated in the factory, but we just go and check for a given transducer, all these constants are correct. Once everything is there, and then we go to the next item, basically. Okay. Now, when you go to the next button, it will open up this interface. And again, like you can check all these important parameters, make sure that the parameters are right. And then when you click this button, what the instrument does is it actuates the transducer and moves the center plate. I've shown in the talk, like in the move the center plate and measure the displacement response. Okay. So the center plate is basically supported by the spring. As you move the center plate, you're actually moving the spring, and the spring has a stiffness. So if you multiply the stiffness times the displacement, is basically force. Now we can equate that force to the force it is being generated electrostatically, and with that we can calculate what is the electrostatic force constant is. So that is what is been done. Okay. So let me, yeah. So when I click the button, it's going to go start the test, and you can see that low displacement curve. Okay, now you can see that it started applying the load and measuring the displacement. This is the low displacement response that you measure, and after measuring this low displacement curve, and like I mentioned, that you measure the electrostatic force, and then you calibrate against the the spring force. This is what it is done. Basically, you have the electrostatic force, and then this is the displacement. You can see that the calibration is pretty linear and it is straight, and then you can fit this curve, and from that fit you can calculate what is the electrostatic force constant is. In the talk I've shown you basically force is basically proportional to a constant times voltage square. That constant time is what we are measuring here, and that constant changes with the displacement. That is what we measured over here. Okay. So now we will go and accept the test. Okay. Okay. Now we are done with the calibration. The next step is to go and position the transistor strip underneath the so when you click this button, basically what it does is it brings the sample underneath the tip, and then sometimes it will give an option to home the stages, because it has been already homed, so I'm not going to do that. So now what we do is basically we'll press the button next, and then go to the next menu. Here you can see there are two options. You can do the experiments from optics position as well as the SPM position. Most of the time we would like to do it with the SPM position, so I'm going to go select that option. And then you can also see here a window where you can see put the sample height. So before you do the experiment, you measure the thickness of the sample. That is the information you put over there. Okay. So now, okay, so optics or SPM. And then so this sample is at center. There are 5 samples. You can put 5 samples in this setup, but I put the sample at the center, and you put the sample thickness, and then you press next. So the sample, you can see it is at the center. It has been integrated as selection 1, and then you go to the next. Here you have an option where you can change the position after you find the sample surface, but I'm going to go leave it there. And now in this window, if you can see that there are certain parameters needs to be put. The important parameter is the contact force, and once you put the contact force is necessary. Basically what is happening is, as the tip makes contact the sample surface, it has to maintain a certain amount of force. So that is the force that we are going to give here as contact force. So when it makes contact, when it feels that 2 micronewton force, it will stop. Okay. So after that, like for example, when you put the number there and then you run, okay, so it's a 2 micronewton force, and then now if I go click find surface, the tip, so what it will do is basically the sample will be underneath the tip, and the tip is going to go approach to the sample and try to make contact with the sample surface. Before doing that, it will ask you whether the tip is actually on top of the surface but not in contact, and then you say yes, then it will start to approach. Okay. So now when you press the find sample, so you can see there is a window here. So in that window, you can see this is basically this kind of showing you where the piezo is. Right now it is at the middle, but as you want to approach and make contact, what we do is we extend the piezo with the transducer, and with the extended position, we approach to the sample surface. The idea is like when the piezo is extended and when the tip makes contact, we can pull the piezo back quickly so that it can be away from the surface, or make the kind of contact with the required force that we need. Okay, that is why we extend the piezo and approach to the sample surface slowly. As soon as the tip makes contact, the piezo immediately will pull the transducer away from the surface. That you can see here. Okay, so it will take few seconds. Okay, you can see that so it came back to closer to the surface. It is asking whether it is underneath the tip. I say yes. Now the piezo will extend. and then the transducer is stepping towards the sample surface. Okay, you can see the sample force, and I asked for 2 micronewton. When it consistently measures the 2 micronewton force, you can see the piezo will pull back. Okay. You can see that in a few seconds. Okay, you can see that the tip is closer to the surface. It is approaching, stepping through. Okay, and then when it finds the surface, you can see that piezo is going to pull. Just give me a second. Yeah, you can see the piezo got pulled, and then it is kind of a repositioning the piezo such that the force between the tip and the sample is almost 2 micronewton. Okay, so now you find the surface. Then now you know where the surface is with respect to the home position. Now it is, when you say you're done, it will come to this window. Okay, here you have 2 options. You can do the experiments from the because you already found the surface. You can immediately go and start the experiment. You can do an inundation experiment, but we wanted to find we wanted to see the surface. We wanted to get a scanning probe microscopy of the surface. So what we are going to do is we are going to go select the SPM imaging. That will take a few seconds. Okay. Okay, now, yeah. So now we are in. Okay, so now when you click the SPM imaging button, okay, you will come to this interface. On this interface, you have options. Basically, this is the SPM imaging interface. In this image, this is the window for the SPM image. Okay, and below that window, you have an option here. What is the size of the scan that you wanted to do? Typically, you can go up to 76 or 80 micron, but we wanted to initially like do a small scan. This is 20 micron. You can put any size that you want. 20 micron, 1 micron, about 70 microns. So in this experiment that we are going to do, it will be done at 20 micron. Okay. 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 20 micron. So on this side of the interface, you have a couple of buttons. What it does is basically this disengage, engage. If you want to momentarily engage or disengage the tip from the surface, you can do that by activating that button. And then below that, you have scan parameters. This scan parameters is basically how fast you want to scan. We can go up to 10 hertz scanning. If you do it depends upon the size of the image that you want to do. When you do 20 micron, the maximum scan size is about 3 micron. So 3 hertz. Okay, so what it means is basically it scans one time, like it goes full and then comes back. Okay, and now so with 1 hertz, we can select, and then you say that this is the force that when you do the scanning, the force between the tip and the sample that it is going to maintain is about 2 micronewton. You put that over here as set point, and then this is a feedback loop. Basically, what we are doing is we are scanning with the tip left and right. And then while we are scanning, we are trying to maintain this force, which is called the set point that we are trying to set. Okay, but to maintain that set point, you need to have to do a feedback loop, right? That feedback loop has kind of integral gain. That is the parameter over here. So you put the right integral gain, and then all these parameters are done. Then you can go and start SPM imaging. Okay. Okay. Okay, now when you do the engage and when you do the image, then you'll pop up this window, and then it will start to image from the bottom to the top. Okay, then you can see that line by line. You can see the line profile here. As it images, you can see that image profile line by line, and then it has been constructed to give you the 2D image of the surface. Okay, so it's going to, now it is scanning from the bottom, it is going to the top. This is a 10 by 10 micron size image. No, sorry, 20 by 20 micron size image. Okay, now you can see that as the image is forming, this is a fused quartz sample, and you can see there are some dirt on the surface. Okay, you can see that. So, so what we are doing is we are scanning with the tip left and right. So we are scanning with the tip left and right. And then below that, you have scan parameters. This is a few squad sample, and you can see there are some dirt on the surface. Okay, you can see that. So, so what we are doing is we are scanning with the tip left and right. And then below that, you have scan parameters. This is a few squad sample, and you can see there are some dirt on the surface. Okay, you can see that. Once the SPM image is done, then you can use that image to select where you want to do the indent. Okay. So let it finish the image. So imaging is almost done. So now what I can do is I can go and select method from where I want to do the experiment, or I can do a single indent experiment by clicking this button. Okay. So when I select the piezo automation, what it does is basically you can do multiple indentation at one stretch. And so I'll come to that a little later. Let's go and do single indent first. Okay. So by clicking this button, it will open up an interface. So when I click, the tip is positioned to the center of this image. Okay. Now you have this interface, and this interface you can build the whole indentation profile. For example, you have options to program the load and unload profile. Here, for example, there are 2 segments. All the experiments are done segment by segment. I can create a number of segments, like 1000 segments if I want to. For example, here I'm starting with 0 load, and then it goes up to 8000 micronewton load in the first segment, and then immediately unloads to 0 load in the second segment. That is what is being shown over here. Okay, and then you can add segments or delete segment from this interface, and you can also go change the load or the displacement with that interface. Okay. Okay, now so this is 8000 micronewton load. I'm going to go select that as the load that I want to do. It's first segment, and now let's do a single indent. By perform single indent, you can see this. So what you see is basically a window where it is measuring the displacement as a function of time. From the displacement as a function of time reading, it measures the drift. So when the drift reaches to certain number, for example 0.05 in our case, sometimes maybe higher depending upon the room condition, it will immediately start doing the experiment. Here at least now it is about 0.075 or about 0.1 nanometers per second. So when it reaches certain parameter that we set as the drift, it will start automatically doing the indent. Okay, just give me a second now. Okay, so now let's go start doing the indent experiment. You can see the load displacement curve, loading and unloading. It's a real-time view of the load displacement curve. Once it is done, it will allow you to go save the indent experiment. So you can go select that and then put the name, whatever that you want, and then save. And then you can see the load displacement curve. This is the load displacement curve that I presented in my talk. From this load displacement curve, we can go and measure the unloading slope and measure the stiffness and measure and calculate the hardness and modulus. Okay. So we're not going to do that now. So let's go back to the test and then go on image again to see the indent image that we created in the first test. And so I'm going to go use the same image parameter because I'm not moving anywhere. So I'm going to use the same image parameter, and then we can start do the imaging immediately. So this is the advantage of in-situ SPM imaging. After doing the indent, I can go on image and see whether the indent is done properly or not. So let's do the imaging again. So if I click the button, it will move the probe to the corner over here, and then it will start from the bottom to the top. Okay, and then you can start to see this line profile again here. And it will take a little bit time to scan and cross the indent. Just wait for a few more minutes, seconds. Yeah. So you can start to see the indent image that we just did. You can see that pyramidal indent. This is a 20 by 20 micron size image, and the indent may be about few microns. That way it looks very tiny. But what we can do is we can go and zoom the indent, and then we can change the size of the image, and then we can see a bigger image. So just give me a few seconds. Okay, so let it scan. Then you can see that zooming. You can see a rectangle when you zoom, and then you go start SPM image. Now it will only zoom that image area, but I think there is an offset, so I'm going to go change that by changing the scan size. Okay, so I see that the offset here now, and you can see on the line by line profile, you can start to see the indent here. So I'm going to correct the offset, change into 4 micron image size, and start again. And then now the offset is corrected, and then you can see the image a little bit distance from the frame. Okay, it will take few seconds to go to the image to the indent side. You just give me a second. So it is scanning again. So when it comes to that indent side, you start to see the indent image, and you can also see on the profile. Okay, you can start to see the profile, that indent profile. You can see this is the cross section profile. That you started to see the tail end of that image. This is 4 micron by 4 micron image. It's a little bit pixelated because of the video. Then you can see the image. Okay. Let it image. Once the image is done, we'll go do the piezo automation next. So you can see a beautiful indent image. So let's move fast. I'm going to go. Okay, now when I do the piezo automation button, okay. Now when I click the piezo automation button, it brings this window where you can go. You can do either array of indent by clicking this button, or you can click the feature that you wanted to indent, the location where you want to do the indent. I'm going to go use the click based method. Okay, so once I click, I'm going to go click couple of locations and then start doing the indents. And I'm going to erase those now because I need to start from 0 to 0 location. So I'm going to erase that by clicking it again. Yeah, it's okay. Now it's erased. So select that part. That is where I'm going to do the first indent, which is the 0 location. And this is the second location. Okay, so 2 indents, and in these 2 locations you will do the indent. And I need to define the load profile. I'll go and adjust the load. Now instead of doing 5,000, 8,000, I'm going to do 5,000. So 5,000 micronewton. It's a 2-second load and 2-second unload. So now, yeah, it will be done on the 0 and 1 location. And I want my start and load to be the same. I'm going to indent. The way it works is basically you start with the maximum load, and then start with one load and then go to the next load progressively to the maximum load, that end load. So I'll use the same 5,000 load for the first indent experiment, I'll use the 5000 micronewton load, and second also 5000 micronewton load, and then save the file as a demo file, and then save. Okay. Now, if I go and click the run script button, it will automatically start doing those experiments under on those two locations. This is the first location that is going to go do the experiment, and then you, again you start measuring the drift, and when the drift settles to 0.05 or whatever that you set it, immediately it will start doing the indents, and then you can start to see that load displacement curve. Okay. So here we are doing the clip based method. We can also array. So now you see the load displacement curve, loading and unloading. This is 2-second loading and 2-second unloading up to 5000 micronewton force. And then the first indent is done. Then it's going to the second indent. It's going to do this drift correction again. And once the drift has been measured, it will go and do the indent, second indent. Okay. Now it's going to go start the second indent. Yeah. This is the second indent. Load and unload. Yep. Now both the experiments are done. It will wait for a few seconds for the scanner to position again. And then once it is done, it will come out and say the experiments are done. And then you can go back to the SPM imaging and to see whether the indents are done in the place where it was supposed to be. Now it's done. Now you exit from here. It will take you to the SPM image window. And then you engage again to image the surface. To engage. So piezo is stepping towards the sample. It will take only 20 seconds now because we already know the surface. Within 20 seconds, 21 seconds, it will find the surface again. Now it's found the surface again. It's in 21 seconds, it did. Now we can go and image the surface again. So by clicking the button, I can start doing the SPM imaging again. And in this image, what you will see is along with this big indent, you can see additional 2 indents where we clicked. Okay. So start doing the imaging again. You can see the line profile. I'm going to speed it up. Okay, there's a second image. You can start to see that. This is where we clicked the first indent, and you can see the second indent appearing. Okay, this way you can select where you want to do the indent experiment, and after the experiment you can go back and image and make sure that indent's been done where you want it, and you can measure the size, and you can get the full nice image of the indent. So this is how we do experiments. I think that's all now I have in this demo video. So I will stop here, and then I believe that this kind of gave you an idea about the instrument interface, how we can do the experiment. And believe me, like this is a very simple interface, very easy to follow. It may take about a couple of hours for a student to first learn. After once they learn, they can go and do whatever the way they want. And it takes, if you look at the interface of our high-strand instrument, anybody views, you know that how complicated it is to operate. But this is we kind of lay down in a way that it's much easy to understand. And so now this instrumentation, the instrument is being used here at the University of Minnesota, where the students are learning about nanomechanical testing. It's there in UC Berkeley. It's there in MIT. So and in US, it started kind of gaining momentum. We have to do the same thing in India. So we started doing that now. So with that, I will stop here, and I will take any questions with respect to this demo part. Okay.
Thank you, Dr. Asif. Very nicely you have explained all this functionality. One question I had: can we actually do any batch measurements on these?
Mhm.
Like,
Yes, yes, you can do that. So for example, let me see whether I can bring back the window. Okay, so you have in this window, you have these 5 positions, position 1, 2, 3, 4, 5. And within that position, this is basically a 10 millimeter sample size, basically. Within that 10 millimeter sample, you can have 2 or 3 samples if you want. And within that, you can do kind of a batch of indents. For example, you can do from, say, 100 micronewton to, let's say, 8,000 millinewton force in one batch, in one array. And then you can also, another batch, you can change those batch. And you can do from one location to next location to next location. You can have 3 or 4 type of samples. You can do all of that. Okay, you can do piezo automation on different samples. Okay, and you can do it batch by batch.
any questions from the participants or from the faculty members?
He has already presented in a nice way, so we don't have much questions.
We have covered. Uh, with that, finally, I would now request Dr. Swati Sharma for the vote of thanks. Dr.
Just one moment, Abhishek, sorry, just to interrupt. So just to add to Dr. Goyal's inquiry, like, on the budgeting, see, Industron and, Bruker, which was earlier Hysitron. So we have the complete range of instrumentation where we can support, our customers in India. It all depends on the funding, on the scale, but it's not compromising on the data output. The data quality that you see in whole range of instrument, that has not been compromised, but it has
Yeah.
been, it has been modeled in a way that we can meet everybody's requirement, research as well as financial aspect.
Yep.
So whether you go nanoguru or we have in-situ instrumentation also starts now from 120K, let's say, like which you can put inside the HCM. Because I see some of the background, like Abhishek and probably Dr. Swati also, she has done a small scale testing. I mean, I was going through her profile. Like I could, guess that you guys are involved into small scale testing as well. So we have like all the, throughout the solution, like from going from nanoguru to in-situ instrumentation.
So now
Thank you.
Swati and Dr. Abhishek, because both of them are expert in this area.
Yeah.
Yeah.
Very
So
good.
yeah, I would now invite Dr. Swati for the vote of thanks. Thank you.
Dr. Abhishek, can we have one group photo?
Yes, sir. After that, we can have. Yeah, sure.
सभी लोग अनम्यूट ये सॉरी वीडियो ऑन कर लेंगे तो अच्छा हो जाएगा क्योंकि
Yeah, Pratik, I would also request you to maybe turn on your video. We can have a group photograph.
डॉक्टर सैयद आप पिन अप करिएगा ना सो दैट यू कैन कम इन द सेंटर
How do I do that? Okay.
Dr. Asif, maybe you can stop presenting now so that.
Yeah, I'm going to stop presenting. Okay. Now.
Yeah, I'm coming. Just one moment.
And other participant, yes, please.
I request all the participants as well to turn on the video.
Yeah. So another thing that I wanted to mention is like we do a lot of workshops and conferences. One of the flagship workshop that we do is called Nanoindentation, and there must be a photo here. You can see that this is we did for 2019. I don't know whether you can see that in the image that I have. So we do that in Trivandrum. We try to bring all the experts in India, be at one place, and we do that for 2 years. And we are planning to do that for 2022 because 2021 we thought we will do it virtually, but we like people to come directly, participate and interact and talk to us. So we will probably be doing it in 2022, early 2022.
We can do in MNIT, so maybe in the month of May or June.
Yeah, we generally do it in around September. Yeah, we'll see how it goes.
You are not such conference in 2020, na. So if you want to do that in maybe in 2 to 3 months, then we can.
Yeah. So the first thing is we are just waiting for the COVID to settle down. Yeah, and then we'll take a call on that. Okay. Good.
Good.
Yeah.
Very
So I
good.
think you already have the photograph now. Second.
Okay.
Yeah.
So
Um,
participants have.
so
Shall I
now,
proceed, Dr. Murati?
yeah.
Okay. So first of all, a warm and cherished morning to one and all present here. And it is my privilege to propose a vote of thanks and acknowledge the contribution of those who have worked towards conducting this session. So first of all, I would like to express my sincere thanks to Dr. Syed Asif for giving an excellent coverage on nanomechanical testings. And also Dr. Pratyank Rastogi for his contribution towards planning this event jointly with MNIT. I would like to express my gratitude to Dr. Professor R.K. Goyal, who is head of the department, for motivating and encouraging us and the students to conduct such department industry collaborative programs. I'm also very grateful to Dr. Abhishek Tripathi to initiate and conduct events of great importance, which will enrich our students and research scholars to derive the advances in characterization techniques and tools. So we would also like to acknowledge our gratitude towards all the participants who have joined and presented their active participation here. Finally, I would like to thank my budding materials engineers from the MedMass team who have been very instrumental in smooth conduction of this program. And their hard work has always been reflecting from the type of programs that we are having here. I hope all of us present here have benefited from this event. And for any further query, it can be addressed later through personal emails. Thank you all.
Thank you.
Thanks.
Thank you very much.
Yep. Thanks, everyone. Yeah.
Thank you. Thank you.
Thank you, Dr. Syed, once again, and
Thank
your
you.
team, and my
Thank you.
young faculty members, and of course, MedMass team also.
Thank you. Okay.
And
Have a good day, everybody. Bye bye.
Thank you, sir.
So,
Bye.
presentation,
Yep.
the participants were present constantly for more than 1 hour.
Oh, that's great.
Yeah.
That's great. We could
That's
hold
good.
them.
Yeah.
Today, despite that.
Okay.
Yep.
Very
Thank
good.
you.
Bye bye.
Okay.
Thank you.
Yeah. Bye. Have a great
Bye.
day.
Bye.
Yep. Bye.